This is the lecture that should have been given on Friday the 19th of February. You'll recall that last time we noted that a system of linear equations which we know can be expressed in matrix form as Ax equal to B, where A is a suitable matrix and X and B are column vectors, has a solution that is to say is consistent if and only if the column vector B is expressible as a linear combination of the columns of the matrix A. And this assertion is essentially a statement of theorem 2.4. which appears on page 89 of the textbook. Here is an example illustrating the use of this theorem. We're asked to determine if the vector one, 5 is a linear combination of the vectors -1, -2, and 2, 3. And if so, we're asked to express 1, 5 as a linear combination of the two vectors. We know from our theorem that this problem is equivalent to a problem involving the solution of a system of linear equations, which we now set up. 1, 5 is a linear combination -1, -2, and 2, 3 if and only if x times -1, -2 plus y times 2, 3 equal to 1, 5 has a solution for x and y. And this in turn is equivalent to the matrix -1, -2, 2, 3 times xy equals 1, 5 as a solution for column vector xy. In this situation, you will notice that this vector over here corresponds to the first column of our matrix, and the second vector corresponds with the second column. Now that we've reduced our problem to solving a system of equations, this is in particular a system of two linear equations and two unknowns, x and y, we have a problem that we can solve easily. This is a Gauss reduction problem. We solve this using our usual method. We form the augmented matrix, and proceed to perform elementary row operations. Let us create 1 in that position there. We achieve that by multiplying the first row by -1, clearly. We'll leave the second row as is for the moment. Now I'm going to replace row 2 by row 2 plus twice row 1. I'm not going to write down here the operations used. So that gives us a 0 there by design. Twice this plus that, -1. Twice this plus that is 3. Let's create a 1 in this position. And then finally, to take us to row reduced echelon form, let's create a 0 here. This, of course, is not essential to solve the system of equation, but it does make things a little easier. And to achieve that, we replace row 1 by row 1 plus twice row 2. -7. Which yields the solution x is -7, y is -3. And so, our conclusion is that, therefore, since our system of equations has a solution, that is to say, is consistent, 1, 5 is indeed expressible, a linear combination of the vectors -1, -2, and 2, 3. So this answers the first part of the question. The second part is to now in fact express the vector 1, 5 as a linear combination of these two given vectors. And the coefficients involved in this linear combination are none other than the solutions here for x and y. So 1, 5 is x, which is -7, times -1, -2, plus y, which is -3 in this case, times 2, 3. So there we've written the vector 1, 5 explicitly as a linear combination of -1, -2, and 2, 3. One can just check that this expression is indeed the correct one. 1 is indeed minus 7 times minus 1, which is 7 minus 6. That's correct. 5 minus 7 times minus 2 is positive 14. Minus 9 is indeed 5. So yes, this is correct. I suggest that you look at example 2.18 on page 88, and it's also worth reading the discussion, which follows theorem 2.4. on page 89.